Hello and welcome to video number 1 of week 2 of Meteorology 107. This week's focus is on meteorological measurements, mapping, and modeling. And to kick things off, our first video this week, what this rest of this video is going to be about, is station models and surface data, where we're going to get literally a ground level view of the atmosphere, what we base all of our things off of near the surface. Next up, in the video after this one, we'll be talking about upper air data, the data that we collect using radiosondes, weather balloons that go up in the atmosphere to sample higher levels, and SKUTs, the particular kind of plot that meteorologists use most often to look at those kind of data. Then we will get after that model forecast analyses where we aren't actually measuring, we're looking at data that we didn't directly measure, but instead we analyze by combining multiple measurements together in a way that makes meteorological sense and physical sense, or forecasts where we take those initial conditions we get from observations and apply equations of motion to integrate them forward to come up with a numerical forecast. The final video will be on radar and satellites, what we use to help measure the atmosphere in ways that we can't just directly measure by sticking an instrument inside of it, but instead we sense the atmosphere remotely. These are big tools for remote sensing in meteorology. And the overall idea this entire week is to look at what data meteorologists use to investigate the weather and how do they do that? How do they go about that process of looking at these data? And so to get right into our first section, we're going to talk about surface observation systems. The gold standard for these systems that observe surface weather data are the Automated Surface Observing Systems, or ASOS stations. These are the kind of stations that you'll see at your larger airports, and they're really, again, sort of the gold standard for surface observing systems. And they're usually done in coordination between FAA, Federal Aviation Administration, and various weather agencies. And we'll go through the instruments that typically these consist of. First off, you'll see way up here is a wind sensor. This is by standard convention at 10 meters. If you notice up here, this may not look like your typical little wind vane and cup anemometer or even propeller fan blade type anemometer. This is actually a sonic that will perform a lot better in ice conditions. So it doesn't freeze up and lock up if you get icing, which you don't want to have happen for your mission critical airport station. Then we also have our temperature and dew point sensors. These are shielded, and by convention, they're at a height of 2 meters above the ground surface. Over here, we have our precipitation gauge that includes some nice fancy equipment to help with control for effects of blowing, as well as taking care of melting any frozen precipitation so that you get liquid equivalents. Then over here we have this funny little sensor that uses optics to help detect what kind of weather is present, various kinds of precipitation usually. We have over here a ceilometer, which measures the cloud ceiling, how far up is the lowest level of cloud surface. And this not only gives us a sense of how much clear air we have, which is very useful for aviation forecasting, but also if we look at that continuously over time, by measuring one point up, we can see all essentially a time series or a profile of all the different clouds we have. And by combining all those together with all different heights, we can actually determine how much of the sky on average is covered, because you almost never have clouds just staying put, you have them moving. So you measure it over time. You can also have an average that looks like what it is over space. Our next sensor over here is a freezing rain sensor. We won't go into that for detail, but know that it has its own sensor. And last one over here is our visibility sensor, which is a very important quantity when it comes to aviation forecasting. So we also have other kinds of surface observation systems that are used in detailed meteorological analyses. Over here we have RWIS. This is our roadway weather systems. And these are the kinds that you'll see alongside the highway when you're driving. We have AWOS. This is another automated sensor system that a lot of times these are your sort of smaller or lower grade airport sensors. Of course, they're still very high quality equipment, but they aren't quite as robust and as complicated of a setup as your ASOS stations are, because these are more prevalent at like your municipal and regional airports. And then we also have mesonets. So certain states and different agencies can, if they have their own funding and their own need for it, they can put together their own weather stations to gather a higher density of data than just what your airport systems can provide. Now, all of these, as you notice, big things is that you have elevated wind sensors. 10 meters is standard. You have them in a clear area, mostly free of obstructions. These RWIS stations don't always meet that just because they're by roadways, but that is in general what they're aiming for. You want clear of obstruction, so you have a clear wind field to sense. And you'll have shielded temperature and humidity instruments. You'll have precipitation. And you'll have various of other utilities that are important for the application. So, for instance, RWIS is usually hooked up to different road sensors. AWOS usually has visibility sensors. And Mesonet usually have whatever application those are deployed for, sensors to address those things. But then we get to how we actually, have the instruments. How do we look at these data? The key thing for surface stations is we use these things called station models. These are the kind of figures that we use to represent an individual station. And here is a general overview of what these station models look like. This link is a really good one. It will be in this video's description and on Canvas. It has the table just breaking down what each of these things are in detail, and the slides that follow this are using figures exactly from that website. This is directly from NOAA. It's a good source. So the first two things to start out with: temperature, always up here on the upper left-hand corner in degrees Fahrenheit when you're using all these in the US. Sometimes there's differences outside of the US. Then we have dew point on the lower left. And then we'll get into these other ones in a bit more detail. Weather as a symbol shows up when you have some sort of notable weather condition. If you just have clear cloudy skies, usually there's no icon there. It's either between temperature and dew point or off to the left. In the center, the circle always represents your sky cover. We'll look at what the different symbols to indicate those are. Your wind is represented by a barb. So this wind, the barb sticks out the direction the wind comes from, because you remember from last week, meteorologists consider the direction wind blows from. You can also think of it kind of as an arrow. So as a rounded head arrow, that this is sort of the tail or the feathers of the arrow, and this is the point. So the wind is going that way. So it's going that way. Up here, sometimes your sea level pressure is represented in the upper right-hand corner. It's in a little bit of an encoded format, though, so we'll get into that in a bit. And rarely, some of these also display pressure trend. That isn't quite as often in a lot of your common maps that you might see online, so we won't address that in detail. But if you're interested, the breakdown of how to interpret that is on this website. So getting into some of those details. Current weather. This is something that, unless you're a meteorologist and looking at these kind of things all the time, you do not do not have to memorize what all these things are, because you'll be able to have these at quick reference. But the idea is that for rain and snow, you get more of these little dots or more of the little icons as it gets more intense. So rain is the little circles, snow is the little stars. Thunderstorms is this funky little R shape with the arrow on it. Showers, where you have more showery precipitation, has this upside down triangle. Drizzle are these little commas. Freezing rain has this swirl to it. Ice pellets, you usually don't see these coming up as often in the automated systems. But fog, thin and thick with these horizontal lines, and haze, those do show up. But again, this is a good table to just have as a reference. Don't have to memorize these. When it comes to wind, this is probably a good thing just to know this interpretation because it helps in reading these plots more quickly. The key idea is that there are 3 types of indicators on these wind barbs. The full triangles or flags indicate 50 knots of wind. The long barbs indicate 10 for each that you have. And the short barbs, half-size ones, are 5. And it's always rounded to the nearest 5 knots. So this is 50 plus 10 plus 10 plus 5 for 75 knots. And you see, again, the barb is sticking out towards the west. So the feathers of the arrow are on the west side, so that means the wind is blowing from the west. So it's a west wind, and it's going towards the east. But again, we say the direction wind is coming from, so it is a west wind. Here we have 2 long barbs, 1 short barb, so that means it's 25. Here we just have a short barb, so this is how you know if it's just a short barb, it won't be at the very end. You always have a long one or a flag at the very end. So if there isn't one at the very end and you just have the little short one, that means it's 5. And if it's closer to 0 than it is to 5 when you round, that's considered calm winds. So we just get this double circle instead. Pressure, I said that's where you get the little funky encoding. This is your process. This is also on those reference websites. So if it's less than 500, then you stick a 10 in front of it. If it's greater than 500, then stick a 9 in front of it. So you're always going to get then either a 5-digit number starting with 10, essentially, or a 4-digit number starting with 9. And then you divide by 10. So you essentially say decimal place, move here. So you always have the last number is in your tenths place after the decimal point. And then you have your sea level pressure in units of hectopascals, or equivalently millibars. So for instance, this example, since 107 is less than 500, that means we have to stick a 10 in front. So 1010, divide by 10. So, or equivalently, move the decimal point. So we have 1010.7 hectopascals, or millibars. So that's your sea level pressure for this station. The last thing, let's just check. Yep, that's the last thing before our review, is sky cover. In general, what you're going to see most often is either a clear indicator, a quarter indicator for scattered clouds, which is roughly a quarter cloud cover, half, about half cloud cover, and this is partly cloudy, 3/4 cloud cover is mostly cloudy, and a full circle is overcast. There's also these 2 ones that you'll see sometimes depending on the system that's used. Sky obscured means that it wasn't able to make a cloud cover determination because of, say, fog or some full way where the sky was actually obscured. A lot of times you'll see also an M instead, where it just couldn't make a valid measurement due to instrument failure or some other random issue. So with all that in mind, let's do a quick little review and interpret this plot. So we have on the upper left-hand corner 24. So that means 24 degrees Fahrenheit air temperature. If we go here, that is our current weather indicator. This isn't a common symbol, but idea going back here, this is your drizzle. So this is sort of a drizzle type indicator. 21, we have dew point of 21 degrees Fahrenheit. Our circle in the middle is 3/4 filled, so that means we have about 3/4 sky cover, or mostly cloudy. Our wind barb over here is pointed off to roughly the southeast, so that means we have a southeasterly wind that's blowing from this direction to this direction. And what we have here is a flag, so it's 50 knots. And then finally, up here on the upper right, we have 992. That's greater than 500, or 500. So we stick a 9 in front. We move the decimal place so that the last digit is the tens place, or equivalently, we divide our whole number by 10. So we get 999.2. So 999.2 millibars, or hectopascals. So we often don't just have a single one of these station models. We end up having a surface plot where we see a lot of these at once, so we get the idea of what the surface conditions are over a wide area. For instance, this is an example of the Iowa Environmental Mesonet's surface station data. And Ames is right over here. So Ames has 68 temperature, 60 dew point, quarter sky cover, roughly southeasterly winds at about 15 knots. And this one, instead of showing pressure on the upper right-hand corner, to make things a little bit easier to read, it instead has contours, so lines of equal pressure, of equal sea level pressure. You see the number here, may be a little bit hard to read because it's on top of the other ones, but it's 1002, or 1002 millibars, or hectopascals. And you can sort of see how these contours vary. So you can sort of see here is the lowest pressure inside the smallest contour, and you get increasing pressure, or you get pressure gradients going outward from there. Another example is you can see a more regional plot. It can start getting really messy. So these you have to, with practice, learn to zoom in, and then you can start picking out interesting details. Like up here in Minneapolis, St. Paul, there's a thunderstorm happening. Or again, we see down here, our Ames station, we still have that same 68 temperature, 60 dew point. So looking ahead, the discussion post for week 2, discussion on weather maps, so these surface plots are a perfect example of that, is available right now. Big reminder is please don't post the same exact plot as another one of your classmates, otherwise you're kind of doing the same thing. The same type of plot, so if you're doing a surface plot from Iowa Environmental Mesonet, that's fine. Just please do not also copy the date, time, and region. So need to be a unique type, date, time, or region. Can't have the same exact plot. This, because we're going to have a reply on it, the reply is going to be you interpreting someone else's plot that's already been posted and new unique little detail on it. The original post needs to be in by Wednesday, October 14th at 11:59 p.m. Central Time, so that we have the full 3 days or so for people to get their replies up. Lecture video 2, again, SKUT's upper air data, and the week 2 quiz are going to be coming within the next day on Monday. So and just looking back at how the first week's quiz go, just want to recommend that maybe it's best to wait to take the quiz until you've either watched all 4 lecture videos or you are confident in the topic from a past class or finding good outside resources for the topics that I've said would be covered this week on that first introductory slide here. So again, we're getting into the thick of things in this class, so please do not hesitate to reach out to me via email. I know many of you have done that so far, and I appreciate that. Or if you want to have it public so that other people that have that same question can also get a reply. Feel free to use our informal Canvas discussions, which you can get to on the discussion page separate from our graded discussions, if you have any Q&A type questions. And feel free to check Canvas for office hours as well. Again, looking forward to going over skew, tease, and upper air data in the next video. Thank you.